Okay, well, welcome back, everybody. Sorry about that as we were switching platforms here. Our next speaker here is YQ. YQ is the founder of AltLayer, and he's going to be speaking to us about MACH, a fast finality layer for rollups leveraging restaking. YQ?
Thanks for the introduction. Yeah, great to be here. And yeah, today we'll just introduce our latest research around this fast finality layer, especially for the Ethereum rollups and by leveraging the restaking. So this is a collaboration together with igon layer and also RISC-0 team. So later on I will show you how this magic achieves. So why we talk about fast finality, especially for Ethereum rollups, because all layer we are building this orchestration layer. Basically for all the different rollups, we help our partners like games and social application and also DeFi applications. During this process, by setting up all the rollup for them, right, we figure out, okay, there are a lot of requirements and demands from them to really build a faster finality layer for bridging services and sometimes and also for their DeFi application services. So on top of the layer we're building, right, as you can see, it's very straightforward. You can quickly launch your rollup via their dashboard. So I think when we get into this faster finality, we need to know what's the current status of the finality on Ethereum and also the rollup space. I believe most of the audience here, right, you are quite into this Ethereum staking space. So as we all know, typically we call Ethereum as the settlement layer. So as a settlement layer, basically we have some very important functionalities. The first one that we all know that we have a lot of this verification logic on Ethereum for different rollups, for example, optimistic rollups and also ZK rollups. Typically, Ethereum really handles all the verification for both sort of fault proofs and also validity proofs. This makes Ethereum really as a settlement layer. Beyond that, we all know that right now in crypto space, we have most of the liquid assets on Ethereum. Not just about Ether, but we also have the wrapped BTC and the various stable coins. In total, like all these assets make Ethereum as the sort of source of liquidity. So either for different rollups or different L1s, typically they borrow the liquidity from Ethereum. It also makes Ethereum as the importance of this settlement layer. And beyond that, as I just mentioned, right, for the other layers like rollups or alternative L1s, they borrow this liquidity basically via the decentralized like messaging protocol or different bridges just to really try to get this source of fund from the Ethereum. And typically when we say the finality, this word, there's a proper definition for it. For example, when we send a transaction, right, typically we say there's a finality for the transaction that so basically, the block that includes this transaction can't be altered or reverted or modified without having the control of supermajority of the network. So then I have a quick question, like for Ethereum right now, after this post, right? So you feel that the finality for Ethereum is 12 seconds. Can you raise your hands? Or the finality is over 12 minutes. Can you raise your hand? Yeah, so that's why I say like most of our audience are the experts in staking, right? So I will show you that because right now, even after post, actually the finality for Ethereum is still over 12 minutes or 14 minutes. So if you look at the details, right now, in the Ethereum system, as we can see, there are multiple blocks, and within a block we have 22 slots. And typical for each slot, you can see that it includes like sort of the transactions within that block. And each slot is 12 seconds. It's precise or accurate 12 seconds. So it's a deterministic, not like before the POS, it's a POW, right? Typically we say it's roughly 12 to 15 seconds, but right now it's exactly 12 seconds. And after that, within one epoch, we have 32 slots. And typically, when we say a block is justified when there are over 2/3 of the validators in a typical committee attested, okay, that block is fine, and we sign the signature. So we call it like sort of justified. And after that, right, after typically one epoch, we can see most of the, honest or good validators, they will just like continue signing the like sort of the slots and confirm that, okay, for the past lot of slots, they are fine. And after that, when we say slot is finalized, typically it's already after 2 epochs. And when we say 2 epochs, right, as you can see, one epoch 32 slots, right? 2 epochs typically it's 64. So after 2 epochs, we can really confirm that, with super high probability that the slot or the block is finalized. So in that case, we say this is the final finality on Ethereum. Typically, it takes like 12 minutes or even longer, like 40 minutes. So in that case, with the latest consensus protocol of Ethereum, FFG, so basically it's really, really confirmed on Ethereum. So that's why sometimes if you use exchange, right, even after post, we can see that, okay, a transaction already included into a slot, into a block, then it should be fine, right? But at the same time, for most of the central exchanges, they still wait for over like 15 minutes if you really look at the like sort of a number. But this finality time is quite crucial to rollups. Why I mention about this? Because like for most of the rollups, right, as you can see, typically we say the finality for rollup is not like the sequencer transaction or execute transaction typically takes like 1 to 2 seconds, but that's not the real finality for rollup. We call it the soft finality. So when we say there's a finality, typically we say the transaction or the block from these L2s or the rollups can be finalized on Ethereum, then we call it like sort of relatively hard finality for a rollup. So in that case, if you look at this diagram, right, as I just mentioned, for rollup typically there are 2 finalities. One is like soft finality. We all know like for Optimism, Arbitrum, or even like latest Polygon ZK EVM and Scroll, they all have this relatively single sequencer to basically precise all the transactions. And after the processing like sort of the transaction, you generate the blocks on the L2. And after that, it depends on the mechanism they use. Either they post the state rule hash to Ethereum first, and after that, they post like sort of the comprised transaction data to Ethereum. Or, like for example, Polygon ZK EVM, they prefer post all the like sort of data to Ethereum first. After that, they generate proofs for that with their proof. After that, it's sort of like they put the proof to Ethereum again for the final verification of the proof. So in whatever cases, right, as you can see, the soft finality mostly is on the sequencer side. Since right now most of the rollups they're using a single sequencer, it's roughly like a trust me bro model. And if for some famous project, right, like this Optimism or Base or even like different ZK rollup, right, we know that they won't leverage sequencer to do malicious stuff like reordering or front running or even double spend. So in that case, the soft finality should be fine, like 2 seconds. But for most of the rollups, for example, we help them to set up, right? There's some gaming companies, they are basically nobody in the crypto space, or some social application. They are new companies. They don't have that kind of reputation like you to really blindly trust them. So then how we solve this issue about the fast finality? Of course, the soft confirmation won't be enough for them. And but at the same time, if we really wait for the hard finality, for example, the sequencer posts the data to the L1 like Ethereum and then do the verification, it typically already takes a lot of minutes, right? And if it's a proper proof system like ZK proof, you need to wait the proof to be posted on Ethereum. That typically takes like half to 1 hour to generate the proof. And for optimistic rollup, typically it takes 7 days for a challenge period. But for a lot of these rollups or the customers we are serving, right, they want something really fast, especially games, right? For the fully on-chain game project, they want to have the similar experience like a Web2, like 100 millisecond latency or like roughly like that. So in that case, how like basically we handle the trade-off for different projects on the Finality requirements. Typically, especially for the general purpose L2s or rollups, right? We are sort of okay with these relatively slow finality or confirmation thing, because as I just mentioned, right, for most of the general purpose L2s, we know their brands. We know that they don't do malicious stuff with high probability. But for some of the new projects, they don't have such high reputation. In that case, we need to find a way to provide like sort of a fast finality for that. So that's sort of like we come up with the idea, okay, we should build this new sort of like mechanism to really provide this fast finality for the rollups, especially the rollups don't really have a very strong brand, like people don't really trust them. It's sort of like the slogan we already say that don't trust, just verify. And designing this fast finality for rollups, right? Typically we have a bunch of like these requirements or goals we want to achieve. Like sort of like we want to have this kind of fast confirmation for rollup transactions without much trust on the entity itself. Beyond that, we want to leverage some cryptoeconomic security to handle the different malicious vectors. And since we already have very diversified landscape of rollups like OP stacks and also some various ZK rollup stacks, we want to basically handle all of them. And also for different runtime beyond the EVM, we also have WASM, MIPS, and RIS5 or different runtimes. We want to handle as many as possible. So that's sort of as I just mentioned, right, with all these background. So that's the real rationale behind this MACH protocol. Basically, we want to have like sort of you can treat it as a middleware layer or something to do this, provide this faster finality for different rollups. At the same time, just want to ensure that we have enough verification resources can provide the trust for different parties without really have the trust on the single brand. And how about the basic idea? The basic idea, as we can see, right, if you don't have all the trust on the like sort of single sequencer, typically the best way for a third party that, okay, I can run the full node. I just re-execute all the transactions and to reproduce the state transition for it. So that's sort of the very basic idea. But as you can see, right, if you want to run a full node for optimize your Arbitrum, typical right now takes you a lot of resources. Like even for the syncing, it's like over 2 terabyte data. So it's quite like sort of difficult. And beyond that, what are the services on top of it you can provide? Typically, as we can see, right, most of the bridges and the cross-chain messaging protocol can be on top of it. Because once you have the fast finality on the rollup A with proper verification and also on the rollup B, so then the external parties can build protocols on top of it, just to like sort of, okay, we already verified the state transitions on rollup A and also rollup B, so we can just pass a message with a lot of confidence. In the real like sort of design and implementation, we sort of categorize the modes into 3 different categories. One is the permissive node, and then is optimistic mode, and also the validity proof mode. For the pessimistic mode, right, as I mentioned, it's sort of like a little bit stubborn way. You just re-execute all the transactions and just to reproduce the state, and just make sure like the MPT tree and also the like state transitions are correct. So in that case, the most like sort of stubborn way is like to run the full nodes for different rollups, but it's not the ideal case because it's too heavy. So that's why on our side we're building the stateless clients for different rollups. And we already have something for OP stats, so soon we can provide for all the audience here just to run the nodes as part of the network to really do the verification and provide the fast finality layer for the public. And beyond that, we also have some interesting tricks on it, right? Instead of re-executing almost everything for the existing transaction and blocks, you can have some optimistic way similar to our optimistic rollups. You can do this, we can assume the sequencer somehow, they always behave like normally, right? They're typically, you are running your own project, right? You don't really have the intention to ruin your own product, right? Except you are doing, you want to do the scam at the beginning. So in that case, we assume the sequencer somehow wants to really perform the correct state transition since the beginning. So in that case, we can sort of run these nodes in the MACH network, right? To monitor these state transitions, and we don't do the active like sort of like re-execution. It's just like sometimes if something wrong, and then we use a method called this optimistic mode. Basically, it's a bisection protocol between the sequencer and also the nodes in the MACH network. So we will identify sort of which like transaction or even the instruction level is behaving wrong. So in that case, we do the bisection across different blocks and identify the block, further identify the transaction instruction inside that block to basically like figure out who's behaving wrongly. So that's a way typically we use for the fraud proof or fault proof in the optimistic rollup. And beyond that, with the collaboration with the RiskZero, we further develop these called ZK fault proof models. Instead of doing this bisection or the fraud proof, a very complex protocol between several parties, we sort of like generate the ZK proof for most of the precise in the middle, just to remove as much interactions as possible. But the cost or the trade-off of that to generate the proofs, right, typically it takes a longer time. For example, for one block, it takes like over 40 minutes, and the cost around like less than $100. But still, compared to the previous model, it's very costly. But at the same time, you can reduce a lot of these interactions between different parties. And then this is the last mode, and this mode is very heavy somehow, as I mentioned, right? Since we already have the ZK proof in place, so in that case, we can always generate a ZK proof for the past state transitions as much as possible. So in that case, instead of posting all the proofs on Ethereum, you can treat MACH network as a middleware layer, or you can treat it as a virtual layer. You can put most of the proofs on this MACH network, or replace it with some other L2s or L1s, just to make sure like you can always get the proper verification from this proof about the state transitions. So with these like the three different modes for the fast finality layer, right? It really depends on the application or the project's purpose. For different purpose, you can leverage like sort of different fast finality mechanism. And at the same time, I just mentioned, right? There's a trade-off between the cost and also the security guarantee you want. Of course, everyone wants to see that, okay, ZK proof is always the best, right? So we can do all the like sort of proof generation and verification, just make sure everything is executed correctly. But the trade-off that the prover cost is very high. Like every month, probably just for the prover, you need to pay like around $10,000, something like that. But at the same time, if you want to like reduce the cost, you can leverage some optimistic like sort of verification mode, right? In that case, the costs are very low. You just need to run some normal validators and for it. But at the same time, you don't really have the same guarantee of the ZK proof. So as one of the first implementation for this fast finality layer, we leveraging like sort of these eigen layers design by running some of the MACH network nodes at the AVS operators. So basically, we borrow the security guarantee from the eigen layers and then use these security guarantees as the bond for these AVS operators for the MACH network. So in that case, as you can see, right, if we put these AVS operators back into the three modes I just mentioned, right, if typically they are behaving correctly, right, if they are behaving wrongly, you can see there is a slashing mechanism. So with a proper proof, like basically can show that these guys are behaving wrongly, and we will slash this sort of the bond from the borrowed from this igon layer restaking side. The existing status as showed to you, right? We already have this proper fast finality implementation for some of the rollups which we can compile into WASM, and some of them actually like this OP stack and some other rollup stacks. So in that case, for the audience here, if you would like to try out this kind of fast finality operator, right? Like very soon, probably next month, we will roll out some detailed tutorials and instructions for you to register as this operator, as you can see, right? And after that, you can opt in via the platform and by running some of these operators and to do this either the optimistic way verification or do some like very heavy ZK proof generation. As the conclusion, right, for a lot of existing general purpose L2 rollups, they are probably fun with the very big brands, and basically people really feel that we don't need to do extra verifications for the sequencing. So in that case, like the soft confirmation from the sequencer should be okay. But for the long tail rollups, which we don't know their brand very well, and or some new project, right? So in that case, it's better we do some verification instead of blindly trust them. So in that case, we need to leverage some fast finality mechanism like the MACH system to really provide this extra confidence in sort of the transactions they executed on the rollup side. And beyond that, with this fast finality layer, we can definitely have a lot of interesting services built on top of it, like this bridging or cross-chain or cross-rollup messaging protocols. And yeah, so that concludes all my talk. If you have any questions, feel free to ask. Thank you.